All right, so my name is Jonathan Muckle, just a recent PhD graduate out of informatics. And I'm going to talk to you about a research project, an open source project that's been coming out of the university, a research group. So I want to talk about something kind of real that's come out of the program. And it's been a team project. There's a number of students on the team, as well as my committee. Professor Lawson, Professor Ravi, and Professor Wong kind of overseeing the project. And Paul Oslin has also jumped in to contribute to this as well, to this particular project. Now, this big long title here, we haven't really come up with a catchy name for the tool yet because it's not released. This is something that's still in progress, but it's a benchmarking framework for compressing GPS trajectory algorithms, and I'll explain, kind of dive through and break that out, the different pieces of what I mean by that. But basically, what it is it's, what's the data? What's the heart of this? What are we trying to get at in terms of what this tool does, what this project problem does it solve? And the heart of it is looking at the data behind it. And the data is GPS trajectory data, which is a fancy kind of term that's used for tracing a moving object, tracing a person, a car, whatever it happens to be, tracing them over a period of time. And this data, what it ends up looking like if you map it, is a series of timestamps and points. So it's not just spatial data, the time is critical. It's a critical factor, is that this data has not only where you were, but when you were at a location. So when I'm going to use the word trajectory a lot, it's really your GPS trace, where you've been when you were there. And this data is collected in all sorts of different ways now. When I first started with looking at this data and working with it, I was working at GE Research, and they're tracking hundreds of thousands of trucks, vehicles, and trying to do supply chain management, asset management, being able to understand where some of the inefficiencies are and what's going on in the fleet. And now, smartphones are so much more prevalent. It's been growing really exponentially. And if we look at the number of smartphones that are equipped with GPS, that there's over 1 billion GPS-equipped smartphones on the market. And this number is projected to double by 2015. So the number is really, I was surprised about just the scale of that. And because of that, it's really this amount of data that can be collected, or the amount of applications that can be written using this data has opened up a lot of opportunities, but also some interesting challenges. And this gets at why you might want to reduce the size of this data. So we're collecting tons of GPS data. How are we going to manage it? How are we going to use it? What are we going to do with it? And kind of at the heart of that is to try to compress the data, to make it smaller, to make it in a more usable form. And there's three problems that helps address. One is just the kind of obvious, is kind of like in the compression definition, is reducing the size, just to make it so there's less storage requirements. And if we were going to track 4,000 vehicles or objects over the period of one day, and we're sampling it every 10 seconds, that would be a gigabyte of storage. So it does add up if you're starting to talk about managing large fleets over potentially years and trying to have a historical archive of this data. And I think these kind of get more important as you work down. I'd say that's probably the least important of the reasons why you want to compress. In real systems, there's a cost to it. And the cost is not just financial, but it's also in terms of time. The financial is if you're a lot of times, like at GE, for instance, this data was typically sent over satellite network. There could be systems in place that if you have cell coverage, you use the cell coverage, but you always want to have visibility. You always want to be able to send your GPS location back to a centralized server, so you never have a gap in your coverage area. It's expensive to send data over a satellite network. And just to kind of give you some numbers, if we took that same 4,000 vehicles and we were going to send that data over the satellite network, you're talking about $1.8 to $2.5 million a year to leverage sending that data. But I think even more importantly than that is there's time associated with it. So if you're using a mobile application that's tracking where you are, and you want to send that back to a centralized server or send it somewhere, if you can compress that on the fly, your delay is less. So there'll be some performance implications. The less data you're sending, the quicker you can transmit. So it has that kind of time cost as well. And then I think what is really the most important is kind of on those lines of performance. That when you're compressing, what you're really doing is you're removing a lot of the least important information. You're kind of getting at what's there, what it can tell you. You're getting rid of a lot of noise, kind of redundancy. So you're getting at kind of the core aspect of it. And this is important for running queries, running data mining applications. You want to really be dealing with the core aggregate information. So this is why we might want to compress this GPS information. And now I'm going to show you a visual of what I mean by compression. Hopefully this comes up. So if we were going to go from one of the local colleges and we're going to look at this trace over a period of time, the red is the original trace. This is the trajectory, thank you. The red shows the original core data. You can see each balloon there is showing a real point, where the yellow is the compressed. It's a way of approximating the original data. And as you can see, it uses a lot fewer points to do this. But you lose some information in the process. You're approximating and you're willing to sacrifice some loss of information for a much better compression. And this is actually just showing it in terms of just this particular compression algorithm I use is only doing it in terms of spatial error. But also get at is there's ways of doing it where you take the temporal component into account. So what am I getting at? What's the open source aspect of this? Well, this is a framework. What came out of this research is an open source project that has many different pieces that deals with these compression algorithms, compressing this data. And there's a couple parts of this. There's not only the algorithms for compressing the data, but really importantly, there's metrics. Metrics for evaluating success, for how well the approximations work, to be able to determine how well a particular algorithm solves a problem. So ways of validating success. Data is also a core part of this framework, of this project. The data is something critical because that's really what the inputs and outputs is really data. You're taking data, you're compressing it, and then you have other data. So metrics is a way of evaluating the success, but that input data really drives the process, really drives what you're doing. And so a very common research tool is to create synthetic data for benchmarking purposes. And what I mean by a benchmark is a way of you're having a standardized way of measuring performance, of measuring how well an algorithm, in this case, solves a problem. And so there's different ways of synthetically generating this data with configurable properties for determining how well, determining different ways of feeding in data into this project. And then all frameworks have some sort of default behavior. They're meant to kind of encapsulate some functionality that can be used so that somebody doesn't have to write everything from scratch. So even though it's open source, you want to leverage like this pre-written functionality, and that's where these different executors are part of this puzzle. This is pre-canned functionality that you could leverage to be running and configuring this framework for running different ways. And then a core part of any framework or really or an open source project is you want it to be extensible. You know, as writing this, there's a way of envisioning what people how they want to use it, and have code written to support that. But you want to be able to support other people plugging in different things, and be able to customize what they want to do, and to be able to take it to add functionality that you never did yourself. And so being able to leverage and extend these different parts is really important. Now, I did mention metrics a little bit. And let me show you kind of, to really define that just a little bit more. And that I just want to emphasize that we're not just dealing with spatial error, as I mentioned before. we're dealing with spatial temporal data, which means we're talking about latitude, longitude, and time. And there's this metric called synchronized Euclidean distance, or SED, which is a way of measuring performance or accuracy of the compressed representation of trace, which is in black, to the original, which is these dotted lines. And it's measuring performance based on, my approximation is assuming that at this certain time step, I'm estimating you're here, there's some information loss, you were really here, and what is that distance? As a way of measuring success. So there's all these different metrics that are plugged into this framework for being able to measure accuracy. There's another additional metrics not shown for measuring how well you're compressing, how well you're maintaining that speed information, and also direction information as well. And then there's performance metrics. How well an algorithm maintains how long it takes to compress, and how aggressive and how small that output data set is. So this is all extensible. I don't want to spend too much time on this, but basically, just to give an example, this is an implementation of that particular SED error metric. And what it allows us to do is that somebody can come along with another metric that's not envisioned in this project and say, I'm going to go and I'm going to write my own metric. I'm going to define it. Someone can look at this, and in terms of, I don't know how many people saw that earlier talk about being able to replicate results. Bill Hoffman from Kitware was talking about reproducing research. And that's really what this benchmark is getting at. It's a way that if you write a new algorithm and you want to plug it into this and you want to see how well it stacks up versus all the other algorithms in the field. And you might say, well, I think SED is a really bad way of doing that. I have another way of measuring accuracy. Well, you can come in here and you can grab the benchmark and you can plug in your own metric. You can define your own and then you can just run it. And this allows a way that you could extend this error metric interface for doing that, as well as a way of aggregating that information together. In this case, it's just seeing if you were going to look at maximum SED error, you could define your own ways of aggregating them together. Because typically what you're doing is at the end of it, at the end of recording the results, you're saying for this particular data set, this particular trace, that maybe the maximum SED was such and such. So you're aggregating it, you're not looking at the whole, you're not looking at it from a point-to-point basis, you're looking at the overall trend across the whole entire trace. So being able to allow extensible, extending your own implementation. Now, I don't want to go into the nitty-gritty details, but this project has a lot of different algorithms pre-built. So you could go and you could run it with these different algorithms that have been involved in the literature. People have written ways of compressing this data, and this, and you can say which ones you want to run and configure how you want to run these different approaches. And they all have different trade-offs. Some are better than others. And this idea of creating this benchmark came out of having a new way of doing this, a way that came out of the research group, a particular algorithm that said, okay, this is going to fill a gap in the literature. This is going to compress the data in a way for certain circumstances better than other approaches. We need a way of evaluating how well it works. So we need to compare it to all the other algorithms in the field and to show how it's filling that gap and have a comprehensive evaluation. And so Swish was something that we developed, and it stands for Spatial Quality Simplification Heuristic, and it has the ability to be very accurate and also to be fast. You could run it very quickly, and a lot of the processing happens on the fly. So what I mean by that is if you were kind of on your cell phone or something, for instance, and you're traveling around, a lot of that compression can happen while the data is being generated. Not all of it can't report until after it's done, because it uses old information. But when you're ready to send, a lot of that processing is happening while the data is being collected. And like I was mentioning about, I'll go through this pretty quickly, but you could plug in your own. These algorithms really fall into two different classes of algorithms. Ones that give you a guaranteed compression, rate. So you say, I want to compress to 10% of the size. You can plug in that you want it to be 10% of the original size, and it will guarantee that it's going to compress to that level. That if you wanted to compress to 50% of the size, you just plug in a different parameter and it compresses to that. So that's one class of algorithms. And if you had your own, if you had your own way of doing it that was different, and it met this kind of class of algorithms, you could just extend this guaranteed compression class and implement your own functionality. Another class of algorithms are these bounded algorithms, ones using an error bound. These ones typically tend to be better, and for a lot of reasons, a lot more accurate. What this means is that you want to compress to a certain level. You're not saying that I want the data to be 10% of its original size. You're saying I want it to never have an error rate more than like 50 meters or 20 meters or whatever it happens to be. Now Squish, the algorithm that came out of my dissertation in the research group, has approval guarantees on error as well. So and actually not just error, but SED error, which is an important part. It takes into account the time information. And it would be considered one of this class of algorithms. And this is a different way, depending on which class you extend, there's different behavior that the framework will utilize. So the framework means you're trying to do comparisons. We're trying to compare how well these approaches work. And what will happen is by extending the bounded compression class, we're trying to compare apples to apples. So if we want to report out the results at a compression ratio where it's of 10 or 10% of the original size, it will force the compression to be that, even though these algorithms don't work that way. These algorithms, you give it the error, and it doesn't guarantee anything about the size of the return. And it does that by running it many times and doing a search to adjust the parameters to kind of dial it down to where it would fit in to that appropriate level. So the framework has pre-built functionality for dialing in and honing in on comparisons, for being able to compare these different approaches to each other. As I showed earlier in the talk, another important component of the puzzle was the data coming in. The data is critical. So besides the whole approach of developing metrics, developing ways of compressing, and having the code to support that, it's also really important to have data that you can configure that have certain properties to be able to feed in. And kind of a standard is to do synthetic data to do that. So synthetic data, so it's not real, although we've run these different analyses on real data as well. But synthetic data allows to be able to simulate both really realistic scenarios and also really extreme, weird scenarios. There's no privacy concerns, and it really gets at the replication of results, which is critical for doing this. So this is kind of really getting at what Bill Hoffman was talking about if you want the data to be available, you want the code to be available, and you want the results to be available as well. And synthetic data allows you to configure it in all sorts of different ways, but you're using the same underlying model for creating the data. So you have unlimited ability to generate all sorts of input based on what situations you're trying to configure. Now, the framework, I wrote code for doing a Gaussian generator as a way of doing an extreme stress test of the different metrics. So this is not meant to be realistic. The model here is meant to find really worst case scenario for certain metrics. And say, I want to feed in the data that I know compression algorithms are going to have a really terrible time compressing the speed error, or the SED error, or the heading error, and generate data sets that have tons of variability in those particular metrics. So it's meant to really see how these perform under extreme scenarios. This is in contrast to some other generators. This is an open source generator. The Germans seem to be leading the effort in a lot of these synthetic data generators for generating these spatiotemporal data sets. And this particular generator was built on a model using the road network. And it had a flaw that was outlined by some people I'll mention in a second, that long-term observations of long-term observations of objects are not realized without major changes to the generator's mechanisms. And that was part of this work, was putting in that functionality. So adding to this open source project to make it be able to have these long generated histories. And the people who wrote that quote developed one model that is really mature and state-of-the-art and the most realistic for generating data as well. And this is also open source. It uses the Secondos spatial temporal database system to generate realistic traces. And so the framework can be plugged into these three different generators, pulling information depending on what you're trying to generate, what you're trying to show. And to be able to run this, if you grab the code and you're plugging away with it, everything is supposed to be, you don't have to write it. You can grab it and you can execute it, and you can generate everything from a configuration file, saying where the data is, the output, which algorithms you're going to run, and some of the properties for configuring them. And as I mentioned before, there's different ways, different styles of executing certain default behavior, depending on what you're trying to compare. And I mentioned briefly what some of those might be if you're trying to fix a compression rate, what some of the results would be, some of the metrics. So everything's driven from a configuration file. And what that allows us to do is, this is the architecture of it, is if you pass in a configuration file, it'll be parsed, the system will parse it. It will go to some sort of coordinator that then delegates out the work. So if you were going to run this and try to run this benchmark really exhaustively on tons of data with tons of different configuration and just be looking for weaknesses and trade-offs across a lot of really large amounts of information, you could end up delegating this work out to multiple servers to be able to have this to run and have the results be either stored in a shared database or stored on some sort of file system, so you can configure where these things go. Anyway, I blew through at the end there just in the interest of time, some of those details, but I think it's important to kind of just talk about a little bit of where this is going. So this code is not released yet. It's really it's completed, but it's just kind of the finalizing some of the details, cleaning it up a little bit. Some of the documentation that's not just in like scholarly articles, but something that's meant to be more concise and readable to just someone who wants to just get up and running quickly. And then also working on some of the demonstrations and outreach, some plans in terms of how to kind of get people to start using this. In particular, Professor Wong has a lot of ideas and connections in the database community who are kind of interested in spatial temporal data. And then so some of the enhancements. I've seen some scenarios before, people put like a web interface, a front end to it, so someone can just go in there and just kind of click a couple configuration properties, hit submit, thing will run, and either if it takes a long time, email the results, or spit them back to you. And I think that's a way of kind of getting people to start using it. And then also, the other thing I didn't mention is that when the results can be shared in terms of visualizations, charts that we automatically generated to be able to see how well the performance of different approaches, how well different algorithms work, and be interested to make them more interactive and more customizable. And just quick acknowledgement, just in terms of some of the funding. This work came out of the Research and Innovative Technology Administration, part of the UTRC, the University Transportation Research Centers program, and also Professor Wong's NSF Career Award and the University of Albany Faculty Research Awards program. So, thank you, and I'd be more than happy to answer questions, time dependent. Yeah. Anybody?
What do you think about the reproducibility of the decoding, the complex data, I mean, is it should be lossless data or lossless, lossy
All,
compression?
you know, all these algorithms are lossy, and what lossy means for people who may have not heard the term before, lossy means you're losing information. So lossless would be like you're zipping a file. You know you're going to zip that file, and you're not going to have things change when you extract it. The trade-off is if you're using lossy compressions, you can get much more aggressive compression. Now, this framework is really meant for lossy compression. One of the reasons is if you're looking at accuracy metrics make no sense if you're talking about lossless compression because it's supposed to be 100% accurate, so there's nothing to compare. But because, from a technology standpoint, because they're getting a lot better, but GPS devices have typically had a reasonable amount of noise to them. And one way of running these algorithms is you just you can set the error bound to whatever the accuracy of your device is. So if your device tends to be accurate within like 30 meters, you can just set the error bound to 30 meters, and a lot of what you're doing is just throwing away noise. So, you know, but you still, want to have a way of trying to measure how well it, works. It's approximating the original.
Have you thought about integrating it into a smartphone, using the GPS in a smartphone so that somebody could use an app and track themselves over the course of a year or something like that?
Yeah, I kind of hope that preferably what happened is by having this out there, people will start using it, that someone would integrate it in their already existing application. That I think would be the coolest thing to start having it become. I would like Squish the dream would be to have it become like a standard. And I would say that in terms of these simplification algorithms, the one that historically had been was one I didn't really mention in that list, but Douglas Poigers used a lot of GIS applications for simplifying boundaries and things like that. And I think now when you go in towards like the temporal side of it, where you're having time information associated as well, it'd be nice if Squish came in and filled that gap. But have to see how much traction it gets, if any. Yeah.
You said you were interested in hosting on a website. Like, how would you be doing that? Would that be like your own servers and processing power, or how would you be going about doing that?
Yeah, it would just be hosting it on some sort of one of those cheap web service sites. I mean, I have like my own site I've had up there for years that I never really maintain. That it costs. It doesn't. It costs like $6-7 a month or whatever. And I just keep the thing going with just some basic information. And, although one of the difficulties that they kind of look at what some of the dependencies are, because it's got to kick off the process to run, and how much you might be able to do on some sort of other server, you have to kind of look into it. There are hosting providers that allow you to run some more Java applications in the background and things like that. Actually, I should have mentioned, sorry, this whole open source project, this is all in Java. So this is all Java application. And so that would be the core dependencies. It has to run on, it has to be able to kick off a Java program to execute. Okay, well, thank you for your time.
Thank you for joining us for this set of presentations. Now back down in Assembly Hall and Fireside Lounge until 4:15 we have food and just an opportunity to network, meet some of the people who are here. And then at 4:15 in Assembly Hall we're going to be having a panel of different people who work in who do different things with open source and talking about some of the business models